Hey guys, Chill here. Welcome back to Hardware 3D. Today we're going to be looking into mipmapping and anisotropic filtering. And you guys probably have heard of these concepts before, but you may not really know what they mean. And I'm here to shed some light on the matter and show you how to implement that stuff in Direct3D. So, I alluded to this in the previous video where we set up the Sponza scene here. But I mean, if you look at this texture here, this curtain, and look at the texturing. It looks weird. It looks funky, right? This is called a moire pattern. I don't know if I'm pronouncing that correctly, but I don't really care. And it has to do basically with when you down sample a texture. When this object gets very small, we're going to be sampling the texture very sparsely, and it creates artifacts like a moire pattern. There's other problems with it, but you can see when we zoom in closely, it looks fine. It looks good. It looks nice. It's only when you zoom out that you start to go down to brown town. And I mean, if we zoom out of this here, I mean, this is starting to look pretty nasty. There's lots of like speckly funkiness here, and it's not good. So, what is the mechanism that causes this issue? So here's a Sponza scene again, but you'll notice I've added an additional texture here. This is just a simple black and white striped texture. I'm going to rotate it to face this way, and I'm going to push it back so that it is into the light a little better. Let's zoom in move forward. Yeah, so now it's nicely lit. Now we can see it great. It's all nicely textured. It's a stripe. It looks a little funky when you move left and right, and that is also perhaps an aliasing issue, if you will. But let's see what happens when we zoom out a lot. Okay, it's getting a little weird. It's getting weirder. It's getting very weird. And now we're entering the twilight zone because the stripes are getting bigger even though we're moving further away. Now it's completely black. But if I move a little bit, it's white, and it's black, and it's white, and it's black. And it's all flipping out, and it's crazy. This is not what you want in your game. And this is also just a very straightforward case of aliasing. Texture map minification, aliasing, you got it right here. Now the mechanism of how this happens isn't too complicated. Let's say you got a texture here. This is the texture that we were just using, and you are drawing it with a little bit of minification. And let's say the samples, here's how they fall. The texture is going to be sampled regularly to figure out the colors for the plane or whatever, the geometry you're drawing. So we're going to sample it regularly, and let's say it's minified such that the sampling happens like this. You basically got one sample for every stripe, like so. And you're going to get a striped texture. Basically, every stripe is going to be 1 pixel wide, because you're only doing one sample per stripe. Now, let's say you zoom out quite a bit more. What happens? Well, now, perhaps your sampling looks like this. Again, regular sampling. But every single sample that you take falls on a white portion of the image. So when you sample like this, all of a sudden your geometry turns completely white. And then if you were to say, rotate your head by, 1 degree or something, now the samples are falling on the black places. And so now it turns completely black. And that is basically the effect that you saw there that I just demonstrated. And obviously this doesn't make sense. Like if I were to zoom this image out by a ton, let me just do this here. Transform. And I'm going to do it in Image Editor. We're going to minify it by a lot, and we're going to click this, and what happens? It turns gray, which is what you would expect, because when something that has a bunch of, different discrete colors is zoomed out a lot or pulled away far into the distance, all those colors kind of blend together when they reflect off the object and hit our retina. I mean, that's the idea behind the pointillism art style, right? You've got lots of like discrete dots of different colors, but when you look at them from a distance, they all kind of blend together. So from this, the solution should be fairly easy to understand. What you should do is before you sample the texture, you should take groups of pixels and average the color of all these pixels and reduce that down to a single pixel. And so you create a smaller version of the texture where all these pixels have been averaged together, and then you sample that smaller texture. Now, how many you average in a group and how big the resulting texture is depends on the amount of minification. If you're reducing by 2, then your resulting texture will probably look something like this, and you will be averaging 2 by 2 groups of pixels. So those groups of 4 pixels will be averaged, and they will determine pixels in this texture, which will then be sampled. Now, one problem with that is that if you have to do that reduction, that averaging of all the pixels in the texture every time you wanted to sample from it, that would be a lot of work, wouldn't it? That would slow down your graphics card quite a lot. So what we do is we actually pre-generate an entire chain of those smaller images. And that's what a mipmap is. And it looks like this. You have the original image, and then you've got the image that's been scaled down by a factor of 2 in each dimension. And then that one has been scaled down by a factor of 2. So this is a factor of 4, and then 8, and then 16, and so on and so forth. And you generate all the levels down to a 1-by-1 image, usually. And it seems like, generating that many images would be a lot, but remember, they're getting 4 times smaller every time. So the additional overhead isn't too much. You can see it here, it's a convergent series. It converges to about 1/3. So you have to use 1/3 extra texture memory, but then you don't have to perform that averaging. You can see here in the Wikipedia article, they have an example image, and it shows no mipmapping, and you have the weird patterns happening there, and here's no patterns. That's the moire pattern, similar to what I showed you with the curtain there. Here's another version of it. You can see it's a whole bunch of stuff. So basically we have 2 tasks. We have to generate this mip chain, this chain of mipmapped images, and Direct3D has plenty of support for, managing textures as a chain of mipmaps, and it also has functions for automatically generating them on the GPU side, which is nice. So you got to create the mipmaps, and then you've got to tell it when it's sampling to use the mipmaps. So in the Git history here, we see my first try here causing a little bit of an error. So you can see the only file that I changed was texture.cpp, and that's the bindable. And the main thing here is we are going to be calling generate mips. Pass it a pointer to a texture view interface, and it will automatically generate the mipmaps for that texture. Now, in order to take advantage of that, you've got to, do some settings with the original texture resource. Instead of telling that you want a single mip level, we set it to 0, and that means we want all the mip levels all the way down to 1-by-1. You've also got to change the bind flags for your texture here. You have to allow it to be bound as a render target, because if you're going to be generating the mipmaps, the GPU needs to be able to write back to this texture. So it needs to be able to be bound not only as an input to a shader stage, but also as a final output of the whole pipeline. And then finally, in the miscellaneous flags, there's a special flag for generating mipmaps. You got to set that one up. Beyond that, when you're creating the shader resource view, you can specify the amount of mip levels that view is to be using. And instead of setting it to 1, we set it to -1, which means you figure it out. Use all the mip levels. And when we run that, we get an error. We get the useless error information from the return code, and then we get the better error information from our, DXGI error framework. And the information here is telling us that p initial data system mem cannot be null. Now, to understand this error, it's being thrown right here, by the way, we have to look into the behavior of create texture 2D. So the second parameter here, the p initial data, that's not a pointer to a single structure. It's actually a pointer to an array of structures that describe the sub-resources. Now, when we're not using mipmapping, mip levels equals 1, and so the number of sub-resources is equal to 1. And so what we were doing worked perfectly. But if we're using mipmapping, we're going to have multiple sub-resources. And so we'd have to specify the sub-resource data for each of those levels. But we don't have that sub-resource data. We only have the original texture. What we want to do is we want to fill in just the first MIP layer, and then at the end generate mipmaps to get the rest of them. But we can't do that if we try to initialize it with sub-resource data, because you have to have all the layers already, all the MIP levels. So in the next commit here, we fix that up. I changed, I added a function, calculate number of MIP levels, but I actually didn't need it. I just forgot to remove it. But anyways, so we stop trying to initialize the resource with sub-resource data. We just pass in null pointer in here. In here. And then what we do is after we create the texture, we manually call update sub-resource. And there we copy in the first MIP layer. And the function for update sub-resource is pretty straightforward. Pointer to the resource, the index of the sub-resource, that's the index of the MIP level that we want to copy. It's also possible to update a sub-region of a sub-resource, so you can specify a box and only update that box, but we're going to update the whole thing, so this will be null pointer. And then your source data, and then the pitch of the data, and then the depth pitch is for data, for three-dimensional datas. But since we don't have that, depth pitch doesn't matter, it could be 0. And so you see here, the pointer to the texture to update. We want to update MIP level 0, no box, the source, and the pitch, the data pitch of the source, which is just the width of the source times the size in bytes of a single pixel in the source. And then the slice pitch is 0. So we create the uninitialized texture, and we manually copy into the first MIP level. This portion was correct. And then down here, this was correct. You just call generate mipmaps, and you will automatically get all those other levels created on the GPU. Now, unfortunately, when you do this, if you run it, you will not see any difference in the rendering output. You will not see the mipmaps because there's one more step that you need to do. Not only do you have to create the mipmaps, you also have to tell the sampler to use the mipmaps. So here in sampler.cpp, small changes, you have to set the minimum level of detail and then the maximum level of detail. And if you want to use all the mipmaps, you're not doing anything crazy, you can just set the minimum to 0 and the maximum to the maximum float 32 value. And that will give you all possible MIP levels of detail. And this is generally what you're going to do. You also can add a bias factor that is added when doing the level of detail calculation to offset it by a little bit, but you usually don't want to do that. So generally these are the values you're going to go with, and you set those levels of detail, and now it will use your MIP chain. And when we boot up our scene, we get the glorious MIP mapping. So if we look at the curtain now, look at this. No nasty moire patterns, it's very smooth. And when we zoom in, we get the full texture detail. When we zoom out, that's all being blended together. Or, well, it's not being blended on runtime. It was blended when we loaded the scene, and it's using the properly blended MIP level as we zoom out. Similarly, if I look at the floor here and I zoom out, see it's getting very smooth. We're not getting those weird speckly, nasty things that look like garbage. It's a very nice, smooth transition from, a low level of detail to, as we zoom in, increasingly higher levels of detail. Now this is great and all, but it actually creates another smaller problem that needs to be addressed. Maybe you can see it right now. But allow me just to push the light back. Let me see if I can do this here. Push the light back just a little bit. And we'll bring it down a little bit closer to the floor. Yeah, like that. Now watch what happens as I sink down closer to the floor. Now I don't know if you can notice this, but it's getting extremely blurry in the far distance here. More blurry than you would expect. And it gets worse as the angle here gets closer to horizontal. So when we're looking at it like this, it doesn't look too bad. But when you get at this sharp angle of viewing, the distance gets incredibly blurry. So here's an image showing a very drastic example of that effect I just showed you. So when you're looking at a surface like this, at a very glancing angle, the effect of foreshortening of perspective is going to be very strong. And that effect is going to compress things in the Z direction. So they're getting squished, but they're getting squished more along the Z direction than they are along the X direction here. And so what that means is that the texture isn't really being mapped to a uniformly scaled down version of itself. It's going to be mapped to something like this. But we don't have MIP layers that look like this. We have MIP layers that are square, but just smaller than the original. So what it has to do is it has to choose the smallest one that matches, this smallest dimension here. And that means that this dimension has to be stretched to match this here, and that's where you get that blurriness. The blurriness happens in the left-right direction. And you can see that very apparently in this picture here. These lines here are being smeared and stretched in the left-right direction. Now there's a technique to combat that, and it's called anisotropic filtering. Now the actual details of how anisotropic filtering is implemented in hardware are, pretty complicated and also basically up to whoever implements the feature. But in general, we can say that it works by, instead of selecting the smallest MIP layer that matches the smallest dimension here of sampling, it's going to select a more correct MIP layer for the largest dimension, and then it is going to, on the fly, basically squeeze down or average these pixels. The way it does that is, of course, implemented in hardware with many optimizations and cool shits. But the end result is that you get your proper filtering in the squeeze dimension and you don't lose quality in the wider dimension. Now this ratio of squeezing here, that is called the level of anisotropy. And that level of anisotropy, the bigger the ratio here, the more computationally expensive the operation is going to be on the GPU. So if it's a 1-to-1, then anisotropic filtering will not be necessary. But if it's highly squeezed, then the GPU is going to have to work harder, and it does that on the fly. So it doesn't do more work than it has to. But there is a maximum that it can go up to, and it depends on the GPU, but generally it's 16. So it can be a ratio of 1-to-16 is the best you can get. But you can also limit that in settings with Direct3D. So you can say, you can do anisotropy, but only to a maximum of, a level of 1-to-4. Anything beyond that, and don't try any harder. Now, actually enabling anisotropic filtering in code, that ain't no thing. It's very simple. We just got to edit, again, single file sampler.cpp. And I just want to take the moment here. Let's just recognize how beautiful this is when we want to add features, when we want to change things. We don't have to go digging around in a bunch of different files, changing things. Everything is all nicely encapsulated in its correct bindable, organized. If we want to change the way textures are loaded with mipmaps, we just got to edit texture.cpp. If we want to change how they're sampled, we just got to edit sampler.cpp, and that's it. Isn't it great? Anyways, so now for the filtering method, before we're using bilinear filtering for minification, magnification, and mipmapping, and now we want to use anisotropic filtering. And when you do that, you also have to set the max anisotropy, which is what I mentioned before. How hard are you willing to let the GPU squeeze that bitch? And we're saying just use the maximum level that's defined by Direct3D 11, the maximum possible. So we're going to request the maximum available on our card, which is generally going to be 16. And that's it. That's all you need to change. And here we are with max anisotropy enabled. And we can see the floor is not nearly as blurry as it was before. Look at this. It's much crisper even when we go down to this very foreshortened viewing angle on the floor here. Now this comes at a cost. The GPU is going to be working a lot harder. And when you're making a real game, you'll probably notice this if you've played games before. But you want to let the user maybe tweak that setting themselves depending on what graphics hardware they're using. Because if they're using a low-end graphics card, anisotropy is really going to push their card's workload, and it's probably going to drop the frame rate. And there you have it. There you got your mipmapping and your anisotropic filtering all enabled. All in all, was pretty easy to implement in code. No big deal. But there were some concepts I wanted to go over here. I'm not in the business here of making copy pasta code monkeys. Those aren't the types of people who I make these videos for. I want to make videos for people who actually want to understand what they're doing. So that's why I took a little more time on this topic than would have absolutely been required. And I mean, there's more detail that I could have gone into and I might go into in the future. For example, when we are creating this MIP chain, when we're generating it, for optimal performance, you might want to do it in 2 stages. You might want to first create a texture like this, generate the MIP stages, and then this would be a staging texture. And then you create a second texture, which is an immutable texture that only has bind shader resource. And you copy from the staging, or you initialize the immutable texture from the staging. And the reason why you do that is because the more things you enable this texture to be able to do, the less the driver the more you tie the driver's hands in terms of optimization. So if you create a texture that is immutable and static and only accessible from the GPU and only bound as an input, then that is a very restricted texture and the driver will have more ability to optimize. Whereas if something like this, perhaps the driver might not be able to optimize it as much as it could. So in the future, when we look at optimization, we might also look at creating a staging texture and then creating the final texture. Another issue that I've thought of, but I'm not going to go over in this video, is how normal maps interact with mipmapping, because they're also being mipmapped here, and that's a good thing, mind you, but it does create some issues when you zoom out. You can actually get, for example, specular highlights that are brighter than they should be when you zoom out, and it's not a real big deal here. As you can see, nothing really stands out super bad, but it's something that we might want to look at in the future as a little bit of an advanced topic. Advanced techniques for improving accuracy of mipmapping with normal maps. But again, not for this video. We're done with mipmapping and anisotropic filtering for the time being. In the next video, we're going to move on to, these plants, they look dumb, and we're going to fix them. And also, what the hell is this garbage? It looks like some kind of freaky, I don't know what that is, some alien sludge that is infecting the pillars here. So this isn't working as intended, and we need a new feature, we need a new technique in order to render this properly. Spoilers, that technique is, basically alpha blending or alpha testing, and we'll be looking at it in the next video. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.